Okay, so that's the first part. Now we know if we were given 100 forces acting on the certain particle, we know how to calculate the resultant force. Then it comes to the second question. How about the total forces acting on that particle together satisfy the equilibrium condition? That means Newton's first law applies. Then, using that to Newton's equation, we can get more information to calculate the forces, to calculate the angles, and so on. And that is our second job in this chapter, which is to talk about the equilibrium condition of a particle with multiple forces acting on. So when the resultant force, or call the resultant, or call the virtual one, the resultant equivalent of all forces acting on the particle equal to 0, then the particle is in equilibrium. And that's the definition. And many times we use the reverse way. Let's say if the particle is in equilibrium, then the resultant force equal to 0. Okay? So if the resultant force equals 0, then you can reach this conclusion. But normally we go back. We have this conclusion first from our physical understanding. So if the system or the particle is in equilibrium, then we can conclude by saying the resultant force equal to 0. Okay? And that is what we are going to introduce. If the particle is in equilibrium, what does that mean? It basically, why you have all the resultant force together equals 0? Because that's Newton's first law. Right? So the Newton's first law, the first fundamental principle, is basically talking about if the resultant force on the particle is 0, then the particle will remain at rest. That means no movement at all. Or it's going to move, but have the specific. That's called will continue at a constant speed in a straight line. Okay? So number one is constant speed. Even with a constant speed, it doesn't mean it's in equilibrium. Okay? So in college physics, if you have a particle keep moving with a constant speed, sometimes the acceleration is not equal to 0. And if that's the case, it's still not statics problem. It's a dynamics problem. You may say, oh, how can I imagine if there is a movement with a constant speed, however, the acceleration is non-zero? Well, if you look at a circular movement, right? So for the circular movement, the speed, the magnitude is always constant, but the direction keeps changing. So that's why the acceleration is still non-zero. So that's why they say either at rest, that means no movement at all. If there's no movement at all, then of course the acceleration equals 0. Or it's a constant speed, but you need to give another condition. That's in a straight line. So it's not circular movement. Okay? Anyway, so that's Newton's first law. In other words, if we know if a particle satisfies Newton's first law, that's in equilibrium, then the resultant force must be equal to 0. In other words, mathematically, these are the two equations we can have for two-dimensional problem. Any two-dimensional problem, you have multiple forces acting on this particle. You have multiple forces on this particle. You just collect all the forces acting on this particle. You calculate the x component, the y component of all those particles. You add them together. This one, left-hand side, that's called the x component of resultant force, and must equal 0, because that's Newton's first law. Similarly, you collect all the y components of all forces acting on this particle, and that's equal to the y component of resultant force, and that also must equal 0 in order to satisfy Newton's first law. You may say, wow, that's very straightforward, right? Well, with this, we can solve a lot of problems. It's simple enough, but we can solve a lot of practical problems, which I'm going to talk about. Okay? You can even solve the first picture I show you at the very beginning, this picture. Just use the Newton's first law to calculate those forces in the cable, okay? Which I would like you to think about after we finish up this chapter, right? So back to this one, very important, these are the two equations allowing us to calculate something based on the equilibrium condition at a certain particle. Originally, you have forces acting on somewhere in the physical space. But in order to finally, for us to use these two equations, there is a bridge, a media we need to use, and that is called free body diagram. In fact, those equations are applied in free body diagram. It's not from the original picture, although many people just go ahead to use that original picture. Many times you can do a good job, but the problem becomes too much complicated. You better use the free body diagram. That's why I want to introduce a free body diagram. Before we talk about free body diagram, let's look at the real picture, right? So this is the real picture, 2 buildings, and there's a pickup truck here and trying to unload this wooden weight. Okay, it's probably very heavy so that 1 or 2 people really cannot carry. So what are you going to do? Well, you design the mechanism. So when we are studying this statics, there may not be a good way for us to imagine what kind of design we have. Well, you're going to keep learning things so that finally you have the capability to design something, to unload something. But as a first class, we don't need to know how to design that. But once somebody gave you the design, you can have the capability to analyze and to tell whether this design is good or not. At least this is something you can say. Okay, and that's the static stuff we're talking about. Okay, so somebody designed already for us. Basically, in order to unload this stuff, what you need to do, you need to have multiple ropes or cables. So basically, at point A, you have 1 cable connected with a pulley here, and then 1 person trying to manipulate in this vertical direction. You have another cable or rope, okay, connected at point A and all the way to another pulley here, and then another person is manipulating. Okay, so the question is how many forces each person needs to provide with in a reasonable way. Okay, and that is basically the physical problem. Instead of finally solve this problem, which I'm going to talk about that, let's say if we want to establish point A as that particle having multiple forces acting on under equilibrium condition, we know that we have these 2 forces. We have these 2 equations, right? So we're going to establish those 2 equations based on a mathematical description. And basically, that's called a free body diagram. So number 1, you need to find out that particle. The whole chapter we talk about particle, right? We need to identify which particle we're talking about. We're not talking about the wheels. We're not talking about somewhere else. We talk about this because this is the key particle connecting all the forces. So that's why we're talking about this point, particle A. So we plot particle A as 1 material point. And then we just need to look at this point is connected with outside, including the weight of this wooden box. So then this wooden box, instead of drawing the wooden box, because that's a physics, right? That's a real wooden box. But when you talk about mathematics, then you use a force, just with a direction, going down and write down the magnitude of this self-weight. The magnitude of this self-weight is 736, probably given somewhere. Don't worry about that. And then the direction is going down because the self-weight is always going to the vertical direction, down. Second, you have this rope here. Although a person is manipulated, controlled through here, but this pulley mechanism is to have what we call the frictionless, so that this force is the same with this force in terms of magnitude. The only difference is the direction is different. Okay, is direction different? That doesn't matter because direction is given 30 degrees. So then what you need to do, you gave this force in 30-degree direction, and that force magnitude is called TAC, for example. This TAC is the force this person can provide. Although this person does not stand here, but this is the same because of its mechanism, so that the magnitude of this one equal to this. Finally, you have this rope controlled by this person. Same thing. The direction is going that one with a 50 degree, but the magnitude of this is the same with this. And this all together form a free body diagram. Once we have the free body diagram, you just establish this is the horizontal x direction, this is the y direction. There are 3 forces. There are 3 real forces acting on this particle A. Among these 3 forces, 2 of them are unknown. You use a symbol to represent. The first unknown is called TAC. If you don't like it, you call it another name, fine, or FAC. There's another unknown called TAB. That's a force given by this person in red. So you have 2 unknowns. However, you have 2 equations as well. So that's ideal case, right? When you have 2 equations, you can solve for 2 unknowns. So then the problem is solved. Finally, you can give the conclusion with this design done by somebody else, more experienced designer, engineer, at least you, through this statics concept, you can tell whether this design is realistic or not. For example, you finally end up with this force, TAC, equal to like 1,000 pounds. Can a person provide 1,000 pounds? No. Almost nobody, right? But if you finally end up with this force, which is 100 pounds, well, that's easy. I think most of us can provide 100-pound force. So in order to say finally this is realistic or not, we just need to calculate those forces. Okay? So I'm going to talk about a very specific example just to show you how to use the static to make a good understanding about the real situation. And this real situation, at least in the past, you can see from real situations. Now may not be the real case, because with the new technology, people may not use this way to unload a car. Okay, so let's say there is a car trying to be unloaded from the ship on the ground. Okay, you see the car, the self-weight is very heavy. It's 3,500 pounds. So obviously one person or two people cannot just carry down. Okay, you need to use a mechanism. So again, we're just learning the statics. We don't know how to design that. Let's assume somebody designed for us already. Okay, and this is the design way. So basically, in order to smoothly, carefully, slowly unload this car from the ship all the way down to the ground, what you need to do, you need to make this kind of small mag to carry the car. At the same time, you have this rope or the cable through this crane. Okay, and then you have another cable here, a rope, controlled by this person. This is a real person trying to control, make it very smooth, slow, whatever, right? To make this successful unloading. So in a ship unloading operation, a 3,500 pounds car is supported by a cable. There's a cable. In addition, the rope is tied to the cable and pulled to center to make it stable. That means in equilibrium. The center of the car over its intended position. And what is the tension in the rope? In other words, how much force this person need to provide. Okay? So, if you look at this statement, obviously this is the equilibrium condition, problem, and all things are connected with this point A. So number one, we need to draw the free body diagram at this point A. So what you need to do is, number one, you plot point A first. You plot point A here, and then you look around to see this point A is connected to what are those forces, right? Number one, this point A is connected with the self-weight of the car. Although you have those kind of steel bars, whatever, it doesn't matter, finally end up with a force going down due to the self-weight of the car. So from point A, there is a force acting on point A going down with a total weight called 3,500 pounds, given from this statement. Okay, so this number one, we have a force connected to point A. Number two, this point A is connected with a cable through this crane, right? Okay, and the angle is 2 degrees. That's 2 degrees. That's also very special. You will see. You can figure out why after we solve this problem. Okay, so it's a very small angle, 2 degrees. Fine. So then that means there is a force, right? So there is a force going that direction. And the angle is 2 degrees. You say, well, the 2 degrees here, the same thing, because these two lines are parallel in both vertical directions. So that's a 2 degrees, and there's a force. And we don't know this force, right? We do not know this force. If we do not know it, then what? You give a symbol to represent. You call this is FAB or TAB. It doesn't matter, whatever symbol you want. We call it MAB. Okay, now the reason they call AB because this is point A, this is point B, right? You call AB, fine. So there's another force acting on point A, and then it comes down to this. This person is controlling, centering this situation with another rope. So this rope having 30 degrees, controlled by this person. So then obviously this person is providing another force, and we do not know the magnitude of the force either. You call TAC. Okay, you call TAC, and the angle between this is 30 degrees, and there's no other forces connected to the point A. And then that means this is what we call the free body diagram. Okay, so this is the free body diagram. We are successfully set up. then we're going to use those two equations, right? So we have a free body diagram. We just need to collect all the x and y components and add them together, set equals 0, because that's Newton's first law. Okay. Okay, so then I need to use this one just to show you how we can solve this problem. There's one screen. I used this one before. Well, I don't know, this one we have a problem. That's fine. So let me just go back to look at this. Because I'm supposed to write down the procedures for solving this problem. Now we don't have it. Let me briefly explain to you. Okay, so from this free body diagram, you just make a table, a chart, right? So the first column, you count 3 forces. You count force F1, TAC, TAB. And the magnitude, the second column, the magnitude of this one, 3,500. The magnitude of this force, we don't know it, you call TAC. And the magnitude of this TAB, you don't know it, called TAB. And then, we're going to calculate the x component, y components. Number one, what is the magnitude of this? What is the x component of this one? The magnitude, the x component of this force equals 0, because there's no x component. And then the y component is a negative 35. So it's negative 3,500 pounds. That is the y component of this force. So then we're done, right? With the last two columns, x and y components. We're moving to another force called the TAC. So what is the x components of TAC? The x component of TAC is TAC, which is unknown, the symbol, multiplied with a cosine 30 degree. Okay? So it's cosine 30 degree, that's x component. So the x component is the cosine 30 degree. Y component is TAC times sine 30, but this one is going down. So it's a negative TAC times sine 30. That's y component. Now, the last force, which is called TAB. What is the x components of TAB? The x component of TAB equal to TAB times sine of this angle, 2 degrees. But this one is going to the left. So that's why it's a negative TAB times sine 2 degrees. That's the x component. Y component of this force, is TAB multiply cosine 2 degrees. That's the y component. And this going up, that's positive. Okay? So there are 3 forces, and correspondingly there are 6 components. 3 of them are x component, 3 of them are y component. You add all 3 x components together, and that's equal to 0. That's the first equation. You add another 3 y components together, and set equals 0. That's the second equation. So now we have 2 equations. And how many unknowns we're trying to solve? There are 2 unknowns as well. TAC, TAB. So that's a perfect match, right? So normally the number of equations should be identical to the number of unknowns you're trying to solve. And we gave you those 2 equations, allowing you to solve for those 2 unknowns. So that's perfect. If you ask me how I'm going to solve, well, if you really do not know it, because those are linear algebra equations, in fact, right? You need to go back to review your high school math, because that's algebra, well, even algebra 2, I believe, right? So definitely, if there are 2 equations, and those are the linear algebra equations, there's no doubt you can solve it for TAB and the TAC. Okay, because I do have my handout already. I'm trying to show you the detailed process. So let me just give you the solution, because I also have this one. So next time I need to make sure this, I don't know why it doesn't work. Okay, so finally, after you get these 2 equations, TAB TAB, that's this one, right? So TAB, the angle is given 2 degrees. TAB, the magnitude TAB equal to 3570 pounds. 3,570 pounds. 3570 pounds. That is this one. And then what's the TAC? TAC is 144 pounds. 144 pounds. So then, with those two numbers you calculated finally, you can evaluate whether this is a good design or not. That should be a good design or reasonable design. You know why? Because this person can only provide 144 pounds. And that shouldn't be difficult for a normal person. Right? You may say, well, this one has to be 3,000 something, 3570 pounds. But that's a machine. Right? The machine can provide because this is a crane related. Obviously, that shouldn't be a problem. If somebody designs something with a reverse case, say, okay, in order to unload this car, this person must provide 3,000 pounds. That's not realistic because nobody can provide with 3,000 pounds, one person. So through this way, you can end up with some kind of estimation, assessment, saying this is a good design. You can unload this very heavy car instead of giving a big force, which you cannot. You only need to provide 140 pounds, and that's doable. Okay? And the key, if you really want to study further, the key is this angle. You can think about, if you give another angle, for example, you think about what kind of force this person had to give. Okay? So again, unfortunately, I cannot write down, but I gave you those two answers. Okay? And for all the details, actually, you can look at textbook. This is one of the examples I got from the textbook. Okay, so this is a typical example. Now let me talk about another example. Okay, so this is another example trying to use Newton's first law to solve this problem. Another problem, we have a river here with a flowing rate constantly. So it is desired to determine the drag force at a given speed, that's a constant speed in a straight line. That means Newton's first law must be satisfied. Where the given speed on the prototype sailboat hull here, a model is placed in the test channel. There's a test channel, the river. In addition, there are 3 cables used to align its bow on the channel center line. So that means in this direction with the 3 cables in alignment. For a given speed, again, that's a constant speed, the tension is 40 pounds in cable AB. So cable AB, the magnitude is 40 pounds, is given. And then 60 pounds in cable AE. So cable AE, the magnitude is 60 pounds. These two are given. Now, we need to determine the drag force exerted on the hull, this one, because there's a motor, there's an engine here, so that there's a drag force. Okay. Number 2, what is the tension, what's the magnitude in cable AC? Because there are 3 cables. There's a cable AC here. So among those 3 cables, 2 of them, the magnitude are given. You may say, well, is it realistic to know the to know the tension, to know the magnitude? And sometimes it is realistic if you put a sensor there, the pressure sensor or the force sensor. You can measure that. It's not a problem. Okay, so again, all the forces are on this point. And we know that at constant speed or a given speed, the whole thing must satisfy the equilibrium condition. In other words, we have the 2 equations from Newton's first law. So how are we going to write down those fundamental 2 equations, which are right here? How are we going to do that? Well, number 1, we need to plot the free body diagram. So it's not a good idea just to write the 2 equations from this directly, because actually these are the cables and with a real hull or whatever, right? So we need to plot the free body diagram just based on this. Okay? That's not difficult. Number 1, in this chapter, chapter 2, the free body diagram is always on a certain point, particle. And then obviously, this is point A. I wouldn't imagine you choose somewhere else, right? Okay, so let's say point A. So again, I'm just copying this one from previous case. At the point A, there are multiple forces acting on. Okay, number 1, we have this engine force. That's called driving force, right? That's one we call the drag force. Okay, so due to the engine of the ship, there is a drag force. And we don't know the drag force. But you don't know it, that's fine. You use a symbol to represent. This must be some unknowns, right? So you call FD, force, dragging force. Okay, we don't know it, but we know the direction because this following this direction in the center line. So we have this force putting here, fine. Next, we have cable AE. Cable AE provide a force, okay, in this AE direction given. And the magnitude of this AE is 60 pounds. We know it. The reason is they are here. They gave you 60 pounds in cable AE. So that's why we have 60 pounds. Number 3, there's another cable, cable AB. Cable AB, the magnitude is given 40 pounds from here. So that's why we put 40 pounds, and this angle is given. This is called alpha. Later on we can calculate alpha very easily from the geometry. And another cable is called AC. We do not know the magnitude of cable AE. If we do not know it, what? You give a symbol. You call it FAC, or you call it TAC, whatever symbol you like. And the angle is called the beta. You put the beta here. So no other forces, and this all together form the free body diagram at that point. Right? Okay, so now let's identify alpha and beta. How to identify alpha and beta? Just from the original picture. This is alpha, right? They gave you the geometry from B to this point. What is this point? I don't know this point, but this distance is 7 feet. And from A to this point, that's 4 feet. So from this triangle, you can easily calculate alpha. Tangent alpha equal to 7 over 4, right? So tangent alpha equal to 7 over 4, because from this triangle. And then your punctual calculator will get the inverse, alpha equal to 60.25. Well, this is good. This is exactly following the so-called 4-digit stuff, right? In the middle process. Beta, same thing. Beta is the angle between this and this. The distance here is 1.5. From here to here, again, is 4. So 1.5 divided by 4, that's a tangent beta. Your punctual calculator, you get the inverse, and beta equal to 20.56. This also following the suggestion, right? That's good. Okay, so now we got alpha and beta. We can just write down those numbers. Now we have 4 forces. Okay, we have 4 forces. We just need to get all the x components, y components. We add them together. We got 2 equations. And how many unknowns, by the way? How many unknowns? 2 unknowns. FD is unknown and the FAC is unknown. So in other words, you add all these forces together, you got the resultant force, that's equal to 0. But don't use this equation. Why? Because it's a vector equation. We're not going to use that. We're going to use component equation, right? Okay, now back to this one. That's exactly what we are having here. Okay, so number 1, you have this force. So this is the drag force, right? So it's called FD. What is the x components of FD? The x component of FD is FD. Okay, so that's why you are collecting all the x components. What are x components? This one, x components. Let me count the x components. Okay, so number 1 we have FD. So this all together is the x component. So we have FD here. What is the y components of this drag force? 0. That's why you don't have it. You just add 0 here. Anyway, okay, so that's this force. Number 1. Number 2, this force. We have this force due to cable AE, right? Cable AE. The magnitude is 60. Is this y component, and also is going down. So in y component, you got negative 60. That's a y component. There's no x component of this one. That's why you don't have this 0. You always say plus 0 anyway. Okay, so this is a force. Now we're talking about 2 general forces. One is this. This is a cable AB. Cable AB, 40 pounds. So 40 pounds times sine of this angle, that's the x component. But this is to the left. So 40 times sine 60 something, and then put a negative sign, that should be the x component. And that is this one. Okay, so 40 times the sine of this angle, and then negative sign, your punctual calculator, this is the number. And what is the y component of this one? Y component of this is here. That's a 40 pounds times cosine of this angle, and this going up, that's positive. That's finally end up with 19.84. Finally, we have this force. This unknown force is called TAC. What is the x component of TAC? That's going to be TAC times sine of this angle, 20 degrees. Okay, so sine 20 something, that's equal to 0.35. You punch your calculator and times TAC. So this is the x components of this force. Y component of this force is this one going up. So that's going to be T times cosine 20. Cosine 20 is 0.93 TAC. So now we are collecting all the x components. These are all x components. And we are collecting all the y components. These are all y components. So all the x components together must be equal to 0. So in other words, this plus this plus this equal to 0. That's your first equation. This plus this plus this are the collection of y component. You set them together, add them together, equals 0. That's y component. So equation 1 combined with equation 2 to solve for two unknowns. What are the two unknowns? FD and TAC. And these are the two equations we are writing down here. And combining those two equations, you get these two numbers. And you solve the problem. This time, they only ask you the magnitude of this. You even do not need to indicate direction because the directions are given in the first place. Okay? So, normally, you can follow exactly this, but you really do not need, because I strongly suggest you to make a chart and just write down the x component, y component, you add them together, you add y component together, you build those two equations to solve for the unknown.